The concept of a basis is so important to us that we're going to do a whole bunch more examples to really get the idea of what's going on. So let's begin with one of the vector spaces we met earlier but haven't yet reused, which is the vector space of all polynomials of degree most 3 in a single variable x. So I'll write down the definition. This is the set of all things of the form a0 plus a1x plus a2 x squared plus a3 x cubed for a0 up to a3, any real number. Okay, all polynomials in one variable x with real coefficients of degree at most 3. So there is a basis for this. This has a basis 1x x squared x cubed. The reason for this is that if you have a polynomial which is equal to the 0 polynomial, then all the coefficients must be 0, and that means those things are linearly independent. On the other hand, you can see what a general element of that vector space looks like, and it's very clearly a linear combination of the constant polynomial 1, the polynomial x squared, and the polynomial x cubed. I mean, the general element was literally written as a0 times 1 plus a1 times x plus a2 times x squared plus a3 times x cubed. So those things are linearly independent and they are a spanning sequence, and therefore they are a basis for this particular vector space. Okay, let's take some more examples now. So we're going to take a basis for a subspace of R squared. So I'm going to let S be the set of all vectors of the form A minus A, where A is in the real numbers. So this is a subspace of R squared. I think I'm going to put this on one of your problem sheets, so you'll have to check this for yourself. But in any case, you can check that this really is a subspace for R squared. And what I'd like to do is find a basis for S, because S, being a subspace, is a vector space in its own right, so we can think about finding a basis for S. So let's notice that S has got a element 1 minus 1. So let's call this U. And that is an element of S. Then in fact, if you take U on its own, so just the sequence consisting of just the vector U, then that's linearly independent on its own. The only linear combination of U which gives you the 0 vector is 0 times U. So U is linearly independent. So just the sequence consisting of the one vector U is linearly independent, and it is a spanning sequence for S. The reason it's a spanning sequence is because if you give me any element of S, it looks like A minus A, and I can rewrite A minus A as A times 1 minus 1, so A times U. So every element of S is a linear combination of just the one vector U. The one vector U on its own is linearly independent, and therefore U on its own is a basis for S. Okay, let's try a further example in that line. So we'll take a new thing called T, which is going to be like a generalization of S to 3 dimensions. So this is going to be all the things A, B, C, all the column vectors of height 3 in R cubed, with the property that A plus B plus C is equal to 0. And again, I'm not going to prove it here, but you can check for yourself, or I might even put it on a problem sheet, that is a subspace of R cubed. It contains the 0 vector, it is closed under addition and closed under scalar multiplication. Now there are 2 special elements in here, so U1, I'm going to call this 1, 0, minus 1, and U2 is going to be 0, 1, minus 1. And I claim the sequence U1, U2 is a basis for T. So let's do linear independence. Let's just show that u1 and u2 is linearly independent to begin with. So for linear independence, what do I have to do? I've got to show that if a linear combination of u1 and u2 is the 0 vector, then actually the coefficients in that linear combination were both 0. So suppose a u1 plus b u2 is the 0 vector. Okay, what do you get from the first two elements, the first two entries in the vector au1 and bu2? So the first entry would be a, and the next entry would be b, and the last entry will be minus a minus b. So I've got this is equal to the 0 vector 0, 0, 0, and therefore, just looking at those first two entries, a and b are 0. Okay, that's linear independence. We've shown that if a times u1 plus b times u2 is the 0 vector, then actually those coefficients, a and b, must both be 0. So to do spanning, well, what does a general element of T look like? I mean, I've written it as a, b, c, where a plus b plus c is equal to 0. But that means this variable c, this c thing is redundant, because c is always equal to minus a minus b. So I could write any element in T as a vector whose entries were a, b, minus a minus b. Okay, but that is visibly a linear combination of u1 and u2. That is a times u1 plus b times u2. Okay, so every element of T can be written as a linear combination of u1 and u2. That means u1 and u2 is a spanning sequence for T. So u1 and u2 are linearly independent. They form a spanning sequence, so they're a basis for T. Okay, we're going to prove now an important property for bases of vector spaces. So the property is as follows. Let's suppose you have a vector space V, and you've got a basis V1, V2, V3, up to Vn of V. And then the claim is that every element of V can be written uniquely as a linear combination of the basis. So it can be written as a linear combination of that basis, and there's only one way to do that. Let's try and prove this result. So the fact that every element of V can be written as a linear combination of V1 up to Vn is just because a basis must also be a spanning sequence. So let's just let V be any element of our vector space. Since V1 up to Vn is a basis, it must also be a spanning sequence. So there must be some scalars, lambda 1 up to lambda n, such that V is equal to lambda 1 v1 plus lambda 2 v2 and so on. So I'll just write that as sum from I equals 1 up to n of lambda I vi. And the question is, could there be another way to do it? So let's suppose there is another way of doing it. We'll have another linear combination of v1 up to vn equal to v, and we'll show that actually that linear combination is the same as the one we just wrote down. So suppose that there's some other way to write v as a linear combination of the vi's. So we'll take some new scalars, mu1 up to mu n, and we'll suppose that v is also equal to the sum of mu I times vi from I is equal to 1 up to n. Okay, then what do we get if we equate those two things? So the sum of the lambda I vi's is equal to the sum of the mu I vi's. So if I just do a bit of rearrangement there, I collect together the terms in v1 and v2 and v3 up to vn, And what do I get? I get the sum from I equals 1 to n of lambda I minus mu I times vi. And that will be equal to the 0 vector. So that's just subtracting one side of my equation from the other and collecting the terms in v1 and v2 and v3 up to vn. So what do we have now? We have a linear combination of the v's equal to 0. And the v1 up to vn are linearly independent, Li for short. So if they're linearly independent and you've got a linear combination of them being equal to the 0 vector, that means that linear combination must have all its coefficients being 0. So all these coefficients, lambda I minus mu I, must be equal to 0. In other words, lambda I and mu I are always equal. Right, so we've shown there's only one way to write V as a linear combination of this basis. And that's one reason why bases are useful, because you can represent every element of the vector space uniquely as a linear combination of the elements of your basis. Okay, final slide about bases here. We're going to look at what seems, or what might seem, as a kind of defect of bases. So we talked about the fact that the vector space R squared, for example, has more than one different bases. In fact, every non-trivial vector space will have many, many, many different bases, infinitely many different bases, in fact. So why might it be useful to have more than one basis for the same vector space? Well, what I want to do is I want to think about an example which is going to illustrate the fact that different bases give you different ways of thinking about the same vector space, and those two different ways, or n different ways of thinking about the same vector space, can give you different information. So what we're going to think about is images. We're going to think about the simplest images. We're going to think about some very simple images which I've drawn on this slide. So my images are in black and white, and they just have two squares, like one square on top of the other. And those squares have to be black or white. And I'm going to represent these images mathematically by representing them as elements of R squared. So for example, this one here, I'm going to represent it as an enormous number at the top. So we're going to have a big number at the top which says that the top pixel is very dark, and then a very small, a very negative number at the bottom to represent the fact that the pixel on the bottom is very light colored. So this second image here, we've again got a very dark image on the top. Perhaps it's not quite as dark as the one on the left, so it will be 9,000, very dark pixel at the top rather, 900 there, and a fairly dark one on the bottom, so maybe 100 there. And then here I've got a very light image on the top, so maybe that's minus 1,000 again, and on the bottom I've got a fairly dark image, not quite as dark as the others, so let's say 750. And then here we've got two very light colored pixels, so maybe this is minus 1,000 and minus 1,000 again. Okay, so in this way I can represent my simple images as elements of R squared. So we know that there are two different bases for R squared, well, at least two. I mean, there are infinitely many different bases, but we've met two different bases. The first basis was E1 and E2. So E1 is the first standard basis vector, and E2 the second standard basis vector. And we met another basis as well. So let's call these U1, which is going to be 1, 1, and U2 is going to be equal to 1 minus 1. And these things are both bases of R squared. E1 and E2 is the basis of R squared. U1 and U2 is a different basis of R squared. So let's say we've got some image, and of course we can represent our image as an element of R squared. So if we've got an image A, B, then we can represent that in terms of both of our bases. We could write this as a linear combination of E1 and E2, and we could also write it as a linear combination of U1 and U2. So if we wanted to write it as a linear combination of E1 and E2, we'd say that that is A times E1 plus B times E2. Okay, so the number A, the coefficient of E1, told me how bright or how dark the top pixel was, and the number B told me how bright or how dark the bottom pixel was. So those coefficients that we use to represent our image in terms of this basis are telling us something directly about the image. One of them telling you how bright the top pixel was, and the other was telling you how bright the bottom pixel was. What if I wanted to write them in terms of the second basis? So the basis U1, U2. Well, I know I can do this, and in fact, if you work it out, what you get is A plus B over 2 times U1 plus A minus B over 2 times U2. Okay, and these things here, these coefficients, they're not just some random numbers, they're really telling you something about the image that you're looking at. So, I mean, what does A plus B over 2 tell you about the image, for example? What would that be in terms of the actual image itself? Of course, the answer there, this is the average brightness of the image, so how bright the image is overall. So this first one is telling you how bright the image is, because it's A plus B over 2, the average brightness of the 2 pixels in your image. And what about the other one? What about the second A minus B over 2? Can you think of an interpretation for this one? So one interpretation here would be that this is the difference. So the difference in brightness between the 2 pixels. Between the 2 squares. So you can see here that when we represent the image in terms of these 2 different bases, we learn 2 different things about it. And when we look at it in terms of the second basis, we learned a different thing about the image that we had compared to when we looked at it in front of the second basis. That's the reason which a vector space having many different bases can be useful, because those different bases tell us different things about the elements of the vector space.